Good morning. Myself, Dr. R Kesavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about the topic name is Spectral Studies on Mn2 Ions doped in sodium with Borophosphate Glasses. This is one of the topic from the laser glass spectroscopy. So last and previous session was discussed on the spectral studies on chromium 3 ions doped in sodium lead borophosphate glasses. That covers from the introduction, experimental method and techniques, results and discussion and conclusion of the chromium 3 ions doped in sodium lead borophosphate glasses. Today topic outline of the today talk is on the spectral studies on Mn2 ions doped in sodium lead borophosphate. It covers from the first introduction, that is general introduction, next experimental methods or techniques, results and discussion of the Mn2 doped sodium lead borophosphate glasses, and finally conclusions. These are the we are going to discuss about the today topic. So first, general introduction. So borophosphate glasses are promising material for optical applications because of their good optical properties. This is because of the main is good optical properties, low refractive indices and a low dispersion and a good transparency from the ultraviolet to near infrared region. So it will be a highly transparent from UV region to near infrared region. So it can cover the UV to far infrared up to near infrared region. So this is one of the prominent property of the borophosphate glasses. It is used for the low melting glass holders and glass to melt seal. So it can use for the sealing type applications also. We can use for the borophosphate glasses. Next, transition metal ions are used to probe the glass structure since their outer d orbital configuration. This is one of the important because the transition metal ions belongs to the d orbital configuration. So outermost electrons in the d orbital function have the broad radial distribution. This have the broad radial distribution moving to their potential applications, including radiation sensitive materials. It can use for the radiation sensitive material application they can use, and also you can use for fiber amplifiers and also fiber lasers. So we can draw the borophosphate glasses. We can thin rod type also we can use that you can use for the fiber amplifiers and also fiber laser applications. We can use for the borophosphate glasses doped with transition metal ions. And the glasses containing transition metal ions have been studied extensively in previous studies. They have studied more applications because of the its exhibit the highly transparency from the UV region to near infrared region, and also it having the lot of potential applications for the fiber amplifiers and also fiber lasers, and glass containing transition metal ions have been studied extensively for the different kind of applications. Next, finally, glasses are very versatile material due to the fact that they can be easily doped with transition metal ions as well as rare earth ions also. Transition metal ion means mainly iron 3 plus, Mn2 plus, chromium 3 plus, and nickel 2 plus. These are different kind of transition metal ions, and also rare earth ions so we can use for the different kind of applications, that is dysprosium, samarium, erbium, yttrium, different kind of lanthanide ions. That means lanthanide doped ions we can use for the that is rare earth ions. So these are the different applications and useful for the Mn2 plus doped in sodium lead borophosphate glasses. Next, the ionic conductivity of sodium borophosphate glasses is a nonlinear, depends on compositions. Have borate replaces phosphate. In the case of borate and phosphate replace, and this behavior has been called the mixed glass former effect. So we are using here borate as a borophosphate glasses. We can using the borate as well as phosphate also. That is why you can say as a mixed glass former effect. That means we can use both glass formers. That is one is B2O3. B2O3 borate and also P2O5. So we can use the borate and phosphate. This is the mixed glass former effect. In this study, we can study the mixed glass former effect also by using the sodium lead borophosphate glasses. Recently, borophosphate glasses have been developed for a variety of applications due to their unique properties such as low dispersion, relatively high refractive index, and etc. compared to borate and telluride glasses. If you are compared with the simply singly borate glass and telluride glasses, the borophosphate glasses have the unique properties such as low dispersion, and at the same time highly refractive indices. It exhibits the highly refractive index. These are the unique properties in the borophosphate glasses compared to borate and tellurate glasses. The presence of P2O5. So in the presence of phosphate glasses extends the UV region, that means ultraviolet region, UV region, and reduce the infrared region transmissions. So it will extend the UV region more in the spectral range and they reduce the infrared region of transmission. It will reduce. If you get the 100% of transparency in the UV region, in compare with the IR region, it will be less than UV region. That is, reduce the infrared transmissions. It also reduces the chemical resistance of the glass. So, and also it reduces the chemical resistance of the glass. These are the some important properties of the borophosphate glasses. These are the general introduction in the spectral studies on Mn2 plus ions, doped sodium lead borophosphate glasses. Next, coming to the material selection. In our present glasses, we can use the what type of chemical composition we are used to prepare the sodium lead borophosphate. So the present material selection highlights the fact or advantages behind the selection of borophosphate glass system for the present study. The spectral studies. The present study focuses on the present spectral studies on Mn2 plus ions doped in sodium lead borophosphate glasses. That means we are using chemical composition. What are chemical composition used in the sodium lead borophosphate glass means? Here see the NaPO3 tries 6. This is a sodium phosphate and lead oxide. 30% of 30 mole percent of lead oxide, 40 mole percentage of B2O3 borate glass, and X percentage of MnO2 manganese oxide. That means a dopant. Here transition metal ions MnO2. This is a transition metal ions. Here we are using sodium lead borophosphate. Sodium is NaP, sodium phosphate, lead oxide, boron trioxide, and manganese is the impurity. That means dopant here. That is, we can simply say NaPbBp doped with Mn2 plus ions. So in our present study, that is why we can say the Mn2 plus doped ion in sodium lead borophosphate glasses, where X mole percentage is we are varying from 1 mole percent to 5 mole percentage. So 1 mole, 2 mole, 3 mole, 4 mole, 5 mole. Different concentration of Mn2 plus ions doped with sodium lead borophosphate glasses. That glass concentration dependence we are going to study in the different methods. Next, coming to the experimental technique. So generally the glass preparation is mainly prepared by the very prominent technique is melt quenching technique. So in our glass preparations by the melt quenching technique, first initially we can take the chemical compositions. That is which is the chemical composition mentioned here is sodium phosphate, lead oxide, borate, and max. These chemicals we can choose, and we have to that chemicals we have to weigh the by using the optical balance. We can the batch weight is 8 to 25 grams of weight of the chemical composition we can take, and we can weigh by using the optical balance. After taking the chemical composition, we can keep into the platinum crucible and a melting temperature of 1000 degrees centigrade. Time duration is 30 minutes. So in melt quenching technique, we are taking the melting temperature is 1000 degrees centigrade. Melt duration is 30 minutes. After melting the chemical composition, after we can pour into the free heated, that means free heated brass mold. That is here brass plate we can pour after melting, we can pour into the preheated brass mold. So after pouring the brass mold, we have to keep in at the temperature of 350 degrees centigrade. And that is we can say as the annealing temperature. How you select the annealing temperature means we can take the glass below the glass transition temperature. So we can after we are preparing the glass, we know initially you have to know the DSC. That means differential scanning calorimetry. You can mention the what is the glass transition temperature. In our borophosphate glasses, transition temperature is around 380 degrees centigrade. So we are keeping the annealing temperature below the glass temperature. That is why we can choose an annealing temperature is 350 degrees centigrade. That is selected as a annealing temperature at 350 degrees centigrade. After keeping the annealing temperature at 350 degrees centigrade, we can keep at the same temperature around 10 hours or 12 hours. So this why we are using for annealing means that is main purpose is to avoid the thermal stress and strain. That means we can avoid any air crack or any damage on the glass sample. So that purpose we have to keep the annealing at 350 degrees centigrade. After coming to the 350 degrees centigrade to room temperature, we can stop the annealing temperature and we have to take into the sample to different kind of optical and luminescence measurements. So after taking the glass sample, we can cut the different desired pieces. So how much your requirement you may require, that much we can the sample we can cut the small pieces, and we have to send to the polish also. We can both side we can optically polished glasses. We can send for the different characteristic facilities. That means XRD, dim, same optical luminescence, and different kind of calibration we can measure. But initially we have to measure first step two. After preparation of the glass sample, we can measure the XRD profile. So because we are prepared the glass sample is it shows the glassy nature or crystalline nature, whether it is a glassy nature or crystalline nature. So we have to confirm by using the XRD technique. By using XRD technique, we can confirm the this is glassy nature or crystalline nature. So while measuring the XRD profile, we can observe in the broad peaks. So here we are observing two peaks. Both are visible as a broad peaks. That means this completely shows the glassy nature. Whenever we get in the sour peaks, that shows the crystalline nature. But in our present glass sample shows the broady peaks. That means broady nature peaks. That is why we can say as the prepared glass sample shows the glassy nature. So after XRD profile, we can measure for the different kind of experimental or characterization facilities. So first we need to measure the EPR spectra, and second one is absorption spectra. Third one is fluoroluminescence. That means photoluminescence and emission spectra we can measure. First in EPR spectra, we are using the EPR means electron paramagnetic resonance spectra for the sample were taken, and geode FE. This is purchased from the EPR spectra from Japan company. That is X-band frequency. That means X-band frequency means that is a microwave frequency from 88 to 9.6 GHz with field modulation is 100 kHz. So these are the EPR spectra of the glass sample we can measure at room temperature as well as low temperature also. We can measure by using the geode FE1X ESR spectrometer by operating as a X-band frequency. Next, optical absorption spectra. In this spectra, we can observe the using the spectrometer is Berkeley number spectrometer. That model number is lambda 950. In the wavelength range from 250 to 2500 nanometer, we can scan the optical absorption from 250 to 2500 nanometer by using the Berkeley number spectrophotometer. Next, third one is photoluminescence spectrometer. We can measure the excitation and emission spectra by using the Jobin and Prolog 3 spectrophlorimeter. We are using xenon arc lamp as a radiation source. That means excitation purpose we are using the xenon arc lamp. This lamp is used to measure the different emission spectra exciting with xenon arc lamp. So these are the characterization facilities of the present glass sample. We can measure the EPR analysis, optical absorption spectra, and fluorescence measurements. These are we are measuring in our present study of Mn2 plus doped ions in sodium lead borophosphate glasses. Next, coming to the first resistance discussion, first we can analyze the EPR analysis. First, we can measure the EPR analysis. This first figure shows the EPR spectra of Mn2 plus ions doped different concentration of Mn2 plus ions from 0.5 mole percentage to that means 5 mole percentage at room temperature. So, sorry, this is now not 1 mole percentage. 1 mole percentage to 5 mole percentage. See, starting from 1 mole to 5 mole percentage. So, we are observing a EPR spectra. We are observing a two resonance peaks at a G equal 2.02. Other one is G equal 4.2. G equal 4.3. So, in our room temperature EPR analysis, we can observe the two resonance peaks at a G equal 2.02. Other one is G equal 4.3. So, here observing the 6 lines of alpha pen structure, this mainly belongs to the Mn2 plus ions present in the glass composition. That is why you are getting the 6 line alpha pen structures. So different concentration, this alpha pen lines intensity will be slightly increasing at G equal 2.02. This is the at room temperature EPR signal. So other one is the low temperature EPR signal of the 3 mole percentage of Mn2 oxide glasses. That means manganese dioxide doped with 3 mole percentage of Mn. So we are studying from room temperature to different low temperature. We are using liquid nitrogen as to decrease the temperature from room to low temperature. We are using liquid nitrogen as a source material here. So this magnetic field is varying from 2200 Hz to 4200. We are observing here only one resonance signal at G equal 2.02 with 6 lines of alpha structure. This mainly belongs to the presence of Mn2 plus ions. Mn2 plus ions present in the sodium lead borophosphate glasses. So first we can do show the EPR spectra at room temperature. So in figure 1 shows the room temperature EPR spectra for different concentration of Mn2 plus ions. The EPR spectra exhibit resonance signal with the effective G values G equal 2.02. This resonance signal shows the 6-line hyperfine structure HFS. That means which is due to the interaction of electron spin of manganese ions with its own nuclear spin I equal 5 by 2. That means 2i plus 1. 2i plus 1. That means I equal 5 by 2. That is why we can get 6-line HF hyperfine structure because it have the own nuclear spin I equal 5 by 2. That is why you can get the 6 lines hyperfine structure in the case of Mn2 plus ions. The resonance signal at G equal 2.02 due to the Mn2 plus in the environmental goes to the octaheders. It shows the octahedral symmetry. At higher concentration, resonance signal G equal 4.3 is also observed. In the case of room temperature, we are observing the two resonance signals. First one is G equal 2.02, other one is G equal 4.3. The first one G equal 2.02, you can observe the hyperfine structure, but G equal 4.3, you can get the only single peak of the 4.3 resonance signal. As the concentration increases, the intensity of resonance signal also increases. So here see the figure 1. So concentration increases, the resonance signal intensity will be increasing from concentration of 1 mole to 5 mole percent of Mn2 plus. So that is mainly due to the Boltzmann distribution. It exhibits the Boltzmann distribution law. So a weak resonance signal observed at G equal 4.3 at higher concentration due to the Mn2 plus ions in rhombohedral distortion sites. So G equal 2.03 is mainly due to the octahedral symmetry, and G equal 4.3 is due to the rhombohedral distortion sites. These are the at room temperature EPR signal. Next, coming to the EPR spectra at low temperature. See the figure 2. Figure 2 shows the at low temperature EPR signal from room temperature 295 Kelvin to 133 Kelvin. We are observing only one resonance signal at a G equal 2.02 with 6-line hyperfine structure. So that we are discussing here. The EPR spectra of sodium lead borophosphate glasses of 3 mole percentage of Mn2 plus ions sample were also studied at various temperature from 133 Kelvin to 295 Kelvin. And the spectra shows the figure 2. It observed that the resonance signal intensity decreases with increasing temperature. So temperature increases. See in the figure 2, temperature here from temperature high temperature to decreasing 133 Kelvin. So increasing the temperature, this resonance decreasing the temperature, resonance signal is increasing. That is the mainly shows the Boltzmann distribution law. So that is here says the clearly lower in the temperature, no significant changes in the value of G and the E are also observed. However, a large change in the intensity has been observed for the resonance signal at G equal 2.02. So these are the we are observing from the at low temperature EPR spectra. So in room temperature we are observing two resonance signal at G equal 2.02 and also G equal 4.3. But in the case of low temperature we are observing only one resonance signal at the effective G value is 2.02 with 6-line hyperfine structure. That is mainly due to the Mn2 plus ions in the octahedral symmetry. Next, coming to the EPR resonance signal, we can calculate the number of spins participating in the resonance N. So the number of spins participating in the resonance can be calculated by comparing the area under the absorption curve. Each and absorption peak, we can calculate the number of spins participating in the resonance with the reference of copper sulfate. Copper sulfate 5H2 in the study of the known concentration. So here measuring sample is Mn2 plus ions. Sample is Mn2 plus ions. This is the sample X. Next, CuSO for copper sulfate 5H2O. This is a reference sample or standard sample. Standard. So this both are we are comparing the by using the formula N equal to AX means sample, standard means copper sulfate 5H2. So by using the reference, we can by using this formula we can calculate the number of spins participating in the resonance. So A is the area under the absorption curve. Scan is the magnetic field of corresponding unit length of the chart. G is the gain. P is the modulation field width. Power. P is the power of the microwave source. So where the expand frequency we are using, at that time how much power we are going to apply by using the number of spins participating in resonance. By using this formula only, we can calculate the number of spins participating in the resonance of the Mn2 plus ions. So after calculating the number of spins participating in resonance signal, we can calculate the a flat of log n versus 1 by t. That is, figure shows the 3, a flat of log n versus 1 by t. In this figure, we can calculate the by using this fit 1 by t 10 power of 93 Kelvin versus log n. By using log n, we can calculate the activation energy of the Mn2 plus ions. So in the present study, by using this flat and fitting of the linear fit, we can calculate the activation energy of the Mn2 plus doped sodium lead borophosphate glass. Activation energy is 2.867 into 10 power of minus 21 joules or 0.12 electron volt. From this figure 3, we can calculate the activation energy. Next, figure 4 shows the paramagnetic susceptibility with the temperature. So, temperature versus 1 by psi value. So, by psi, we can calculate it by using this formula. Psi equal ng square beta square j into j plus 1 by 3 into kb into n is the number of spins participating in the resonance, g is the Landau splitting factor, b is Bohr magneton, j is the orbital quantum number, kb is a Boltzmann constant, T is the absolute temperature. By using these values, we can calculate the susceptibility. By using susceptibility 1 by psi versus temperature, we can measure this figure 4 flat. By using this linear fit, we can calculate the psi value. So by using the Curie-Weiss law, we can calculate this psi equal C by T minus theta P. C is the Curie constant, T is absolute temperature, theta P is the Curie temperature, theta P. By using the Curie-Weiss law, we can calculate the Curie constant as well as Curie temperature. So by using the figure 4 flat, we can calculate by using this formula, like this formula, Curie constant C equal 0.114 EMU per mole. Next, paramagnetic Curie temperature theta P equal 120 Kelvin. So by using this figure 4, we can get the Curie constant and also paramagnetic Curie temperature theta P is 120 Kelvin. Next, coming to the optical absorption spectra. From optical absorption spectra, we can observe the 1, 2, 3, 4 peaks from wavelength versus optical density. Here, x-axis wavelength versus optical density, that means absorption. So we are measuring the 4 important optical absorption peaks from ground states to different excited states. That is, here ground state of the Mn2 plus ions is 68s5 by 2. That is the ground state of Mn2 plus ions, because this belongs to the D5 electronic configuration of the Mn2 plus ions. So we are getting the ground state is 6s5 by 2 different excited state. That means WTGT, quartet T1GT, next quartet A1GG2, quartet EGG, and also quartet T2GG. These are the 4 broad absorption peaks we are getting from ground state from 6s5 by 2 different excited state peaks. So the figure 5 shows the Mn2 plus ions in octahedral symmetry. So next one is in the presence of octahedral symmetry, one can predict the few absorption patterns of Mn2 plus ions for visible region corresponds to the transition from ground state to excited state. So these are the different absorption transitions from ground state to excited state of room temperature of the optical absorption spectrum. By using this data, we can calculate the crystal field parameter and Raga parameter. See here from table 1 shows the absorption peaks of the ground state to excited states. So that means here, see the table 1, we are transition from the ground state 6A1GS to different kind of excited states. Quartet T, 2GG, next quartet A, 1GG to this wavelength is first one is 535 nanometer, next 490, 445, 410. These are the 4 absorption bands of the ground state to excited state of the Mn2 plus ions. That wave number energies are different energies. This is by using these values, we can calculate the crystal field parameter dq value and Raga parameters b and c values. We can calculate it by using the Tanabe-Sugana diagram. So by using the reference number 7, we can calculate the dq value and b value, c value. So the energy matrix of the D5 configuration have been diagnosed for various values of dq, b and c, and a good fit is obtained by using the Tanabe-Sugana diagram. By using the Tanabe-Sugana diagram, you can calculate the crystal field parameter value dq is 800 centimeter inverse, and the Raga interelectronic repulsion parameters b and c, that values are b equal 7.15 centimeter inverse and c equal 3 to 15 centimeter. These observed bands are calculated. Energies of the bands are presented in table 1. The calculated dq and b values are consistent with the values reported in Mn2 plus ions in octahedral coordination. So here we compare with the other studies, we can get the different values of the wave numbers energies is from using the bands of the optical observation bands and calculated by using the Tanabasigan diagram, where both are similarly consistent with the energies of the absorption bands of the Mn2 plus ions doped in sodium lead borophosphate glasses. So this is mainly due to the Mn2 plus ions presence in the octahedral coordination site. Next, coming to the emission spectra of the Mn2 plus ions doped in sodium lead borophosphate gas. Say here wavelength versus normalized intensity. We can get this broad emission peak at quarter T1G2, that is excited state to ground state. We are getting that wavelength number is 560 nanometer. We are observing only one emission band at 560 nanometer. This mainly belongs to the green emission. So in the present work, the authors observed a broad emission band at 560 nanometer. This emission band is assigned to the transition from upper energy level quarter T1GT to ground state of 6A1GS. So ground state of Mn2 plus, which is directly responsible for green light emission. So this is the emission spectra of Mn2 plus doped lead borophosphate glasses. This is the, we are using dopant concentration 5 mole of MnO2 glass sample at room temperature. We are observing the green emission at 560 nanometers. So this Mn2 plus ions doped sodium lead borophosphate we can use for the green laser applications also. We can use for the this Mn2 plus ions doped in sodium lead borophosphate glasses. Just finally summarize our conclusion. So EPR spectra of Mn2 plus ions sodium lead borophosphate exhibit two resonance signals at room temperature. One is at G equal 2.02, other one is G equal 4.3. So first one G equal 2.02 is mainly due to the octahedral symmetry. We can get the 6-line half-reference structure, that is mainly due to the octahedral symmetry, that is environmental close to octahedral symmetry. Next other one G equal 4.3 is attributed to rhombic surrounding of Mn2 plus ions. So both are at room temperature. Next other one is the optical absorption spectra exhibits 4 bands characteristics of the Mn2 plus ions in nearly octahedral site. This is compared with EPR signal. This is correlation with same octahedral site. From the absorption position of the absorption band maxima, the crystal field splitting parameters and the Raka parameter also calculated. That values are the mentioned here. DQ crystal field parameter DQ is 800 centimeters, B equal 715 centimeters, and C equal 3215 centimeters. So that also we calculated the crystal field parameter DQ and Raka parameters B and C values are being evaluated by using the Mn2 plus ions in sodium lead borophosphate gas. Next, finally, the emission spectra exhibit single broad band characteristics of the Mn2 plus ions in octahedral symmetry. That wavelength we are observing 560 nanometer is mainly due to the green laser emission. That means the green emission it will exhibit. So this one is useful for the green laser applications also. We can use for the Mn2 plus ions doped sodium lead borophosphate glasses. These are the summaries for the present study. Next, these references are used for the present work. So these are the important references introduction. This work is mainly published in the, this is one of the co-author of in this paper I am myself. So it's N Kiran, R Kesavulu, Suresh Kumar Jailrai, physical. This is published in the 2011 in the Physical B journal. So that we are discussed in the present study in spectral studies on Mn2 plus ions in doped in sodium lead borophosphate. These are the cited references in the present study. So thank you. So next session to be continued in the other topic. Once again, thank you.
Like, share and subscribe. Hit the bell icon for more updates.